morning. So today I will spend my first lecture on doing some integration, contour integration. So before I do some integrals, let me just introduce one topic, that is analytic continuation. We have, for example, if you take a function f of z as 1 by 1 plus z, which can be written in a series. If I expand this about z equal to 0, then I will have n is equal to 0 to infinity minus z to the power n. Now this series will converge for modulus of z less than 1, correct? So series converges for mod z less than. That means for all values of z within the unit circle. For all values of z within the unit circle, the series will converge for any point in this. So this is the complex series. So this particular function, if you see, only at z equal to minus 1 we have a pole. Other than that, there is no other singularity. But now we can ask a question: if I have to write a series about some point outside this region of convergence, can it be done? Can I write this as a series outside this radius of convergence? The answer is yes, you can do it. So let me say that I will expand this f of z equal to 1 by 1 plus z around, say, z equal to I. If I expand around z equal to I, so I will write this as 1 by 1 plus z is equal to 1 by 1 plus I plus z minus. So I have not done anything, I have added and subtracted my I. So this I can write it as 1 over 1 plus I to 1 by 1 plus z plus I by 1 z minus I by 1. This is equal to 1 over 1 plus I into 1 plus z minus I by 1 plus I to the power minus, which gives us a series 1 plus I into sum over n is equal to 0 to infinity minus of z minus I divided by 1 plus I whole to the power. Correct? Now this series will converge for mod z minus I less than modulus of 1, and modulus of 1 plus I is root 2. Okay, so now if I consider this as I, this region is centered at I, okay, and then it has a radius root 2. If this is 1, So root 2 is somewhere here. So you have a region like this. So if S1 was the region, S1 was the region earlier, S2 is the region of convergence of this series. So since you can expand this in terms of Taylor series about I, now all points in this, you can write, this series will converge within this. You can go on doing this, so you can expand about some other point, then you will have a different region. So this series representation you can get throughout the complex plane by analytically continuing with this. But one thing that you can notice that all your circles will actually intersect at the pole. -1 is the pole. So that all circles, whatever circle you write, this -1 will be on the contour. So this is what is called the analytic continuation. You can say something very general here, that if you have two series and their radius of convergence or their region of convergence, if there is any overlap of the region of convergence, then you can say that these two series will converge to the same function. Like in this case, I have a series here which has a region of convergence as S2, and I have a series here which has a radius of convergence as S1, and there is an overlap between S1 and S2. So these two series may look very different, but if there is an overlap of the region of convergence, then they will converge to the same function. Okay? So that is that's what. So instead of, now you choose some point here and then expand it around this point. Like I have, instead of expanding from the origin, I expanded from here. So you choose another point and expand, so you will get another point.
That region also should enclose the pole.
The pole will always be on the contour. It will be on the boundary. It will not enclose it. It will be on the boundary. Within that, it will be analytic. So this is contour integration. Curve. Curve. Contour is a closed curve. Curve need not be closed, right? Curve can be anything. But a contour is a closed curve. I don't know, maybe even in some cases contour is referred to as an open curve also. But in our usage here, when we say we are doing a contour integration, it's always a closed curve. Okay. One important thing is that if you have a function with some singularities, okay, we have talked about poles of higher order and essential singularities. In all those cases, we have seen that if you have f of z, d is z. Now f of z is not analytic. If it is analytic in this contour C, then this is 0. If it's analytic, we have seen Cauchy's integral theorem yesterday, If it's analytic, it is 0. But if it's not analytic, so if f of z has singularity, at z1, z2, z3, etc. from z, etc. at zn, if it has some n such singularities, and if these singularities are poles or poles of higher order or essentially among the singularities that we discussed yesterday, then we can write down this integral as twice phi I into residue at z1 plus residue at z2, etc. residue at zn. So you calculate residues at each one of these poles, and then you will write just residue, sum of the residues into 2 pi I, where R of Zi is residue and residue. Now, how to find residues? Now, residue at Zi is a minus 1. What is a minus 1? Coefficient of 1 by z minus zi in the Laurent expansion around z equal to zi. You take the function, expand in Laurent series around z equal to zi, then you will have the coefficient is the residue. Sometimes you can, as we have seen yesterday, if we have simple pole, at z equal to zi, then residue at zi is nothing but limit z tending to zi, z minus zi f of. And if we have a pole of order m, if we have a pole of order m, what happens? In our Laurent series, we have f of z is equal to a minus m by z minus zi to the power m, etc. We have a minus 1 by z minus zi plus sum over n is equal to 0 to infinity a n z minus zi to the power n. So this is the Taylor series regular part. This is my f of z. So what will be if I write df by dz? What will I have? df by dz is a to the minus m divided by minus m z minus zi to the power m plus 1. Correct? Plus a minus 1 into minus 1 divided by z minus zi to the power 2 plus sum over n is equal to 0 to infinity a n into z minus zi. Okay, so let me put it this way. So first let me multiply this one with z minus zi to the power m to f of z. What I will have? A minus m plus z minus zi into a minus m minus 1 etc. I will have here z minus zi to the power m minus 1 to a minus 1 plus sum over n is equal to 0 to infinity a n into z minus zi m plus n. Correct? If I multiply this with z minus zi to the power m, I have this. Yeah?
Second one, z minus zi whole square.
Second term, the denominator will be m minus 1. So one term will be there. Correct? So this is fine. Now, if I differentiate this once, what I will have? This term will go away. This term will become constant. If I differentiate this twice, this term will go away. Now, if I differentiate this m times, what will happen? This term alone will remain. And then if I take limit, that all these terms will go away. But you can see that, okay, I differentiate it once, this term will be there. I differentiate it m minus 1 times, this term will be there. So, but I will have, if I differentiate it m minus 1 times into z minus zi to the m into f of z, I will have m minus 1 factorial into a minus. So I want a minus 1 finally, that is my residue. So you can get a minus 1 as 1 over m minus 1 factorial to d to the m minus 1 by dz to the m minus 1 into z minus zi to the m into f of. So just like, okay, this of course I have to do this, the limit z tending to z. Why this limit is important? Unless you take this limit, this term will not go to 0. So you can find the residues if you have poles of higher order. But if you have an essential singularity means pole of infinite order. So there, the way to obtain the residue is only by expanding Lorentz series. Okay, so we cannot use this formula. So if you expand in Lorentz series, you can read out a minus 1. So that is what you can do. You have an essential singularity. So this is called Cauchy residue theorem. Using residues, you can actually get the. So the first type of integrals that I will First type of integrals we will look at is integrals of this type. Integral 0 to 2 pi some function of cos theta sin theta is integral 0 to 2 pi some function of cos theta sin theta and dθ. Now you can actually do the following. We know that, so you can write this integral as integral over a unit circle of what is z is equal to e power I theta, the unit circle, correct? Z is equal to e power I theta on the unit circle on mod z equal to 1. So this is nothing but cos theta plus I sin theta. Now we know e power I theta plus e power minus I theta by 2 is cos theta. So we can write down from here cos theta is equal to z plus 1 by z by 2. Similarly, sin theta is equal to z minus 1 by z by 2i. So you write this as f of z plus 1 by z by 2 comma z minus 1 by z by 2i into d theta I e power I theta d theta is dz. So that is d theta is equal to dz divided by iz. So now we have an integral over the unit circle. Okay? So any function of cos theta and sin theta from 0 to 2 pi can be converted as a contour integration over a unit circle contour. Let's consider this example. Integral 0 to 2 pi d theta divided by 1 plus epsilon cos. So you can write this as integral over a contour I dz by z, this is d theta 1 plus z plus 1 by z by 2 to epsilon over this contour, where this contour is mod z is the unit circle. So this can be written as integral over this contour I dz divided by z to 1 plus epsilon z square plus epsilon divided by 2z. Epsilon z, z square plus 1, 2z. So this is equal to I integral over a closed curve dz divided by epsilon z square plus epsilon plus 2z, and I can pull out 2. dz by iz. Put a minus. Now we can ask what is the, so I can pull out an epsilon minus I divided by 2 epsilon integral over a closed contour dz divided by z square plus 2z by epsilon plus 1. Now this quantity z square plus 2z by epsilon plus 1, we should know where are the roots of this equation, that is where the poles will be there. So if you want to know when this will be 0, then z equal to minus 2 by epsilon plus minus square root of 4 by epsilon square minus 4 divided by 2. So you will have minus 1 by epsilon plus minus square root of, so I can pull out 4 by epsilon square, then I will have 1 minus epsilon, 1 by epsilon, 2 will get cancelled. So I will have 2 poles, z1 which is equal to minus 1 by epsilon plus or minus 1 by epsilon. If I pull out, this is 1 plus square root of 1 minus epsilon square, and z2 minus 1 by epsilon into 1 minus, sorry, in this case it is minus, minus and minus plus, and this is plus square root of 1 minus. So we can write this as, so let me call this one as an integral I. So I is equal to minus I by 2 epsilon to integral dz divided by z minus z1 z minus z2. Now, which one of these 2 roots are within the unit circle? That's our concern, because our contour is unit circle. So this radius is 1. So now you can see that there is this factor 1 plus some quantity. If epsilon is small, 1 plus some quantity is more than 1. Okay, so let us, here we have to assume a range of epsilon. Let's say epsilon is between 0 and 1. Epsilon is between 0 and 1. This root Z2 will never be inside epsilon. Correct? 1 by epsilon is greater than 1. epsilon is between 0 and 1, 1 by epsilon is greater than 1. This is more than 1, this is also greater than 1, so this will be more than minus 1. So this root will never be inside this. But this root can be inside this, because if this is sufficiently small, even though this is more than 1, it can come inside this. So z equal to z1 can be inside this for some values of epsilon between 0 and 1, whereas z2 will never be inside this. So we have to call this as minus 2I by epsilon into 2 pi I, the residue of z equal to z1. But z equal to z1 is a simple pole. So residue of z equal to z1 is nothing but limit z tending to z1, z minus z1 into f of z. So what is that equal to? That is equal to limit z tending to z1 of, what is f of z? F of z for us is 1 by z minus z. That gives you 1 by z1 minus. So what is z1 minus z2? z1 minus z2 is minus 1 over epsilon to 1 minus square root of 1 minus epsilon square minus 1 minus square root of 1 minus. So this minus 1 cancels, this is minus 2 epsilon, so this will be 2 epsilon minus 2 root 1 minus epsilon square divided by s. So this is equal to epsilon by 2 square root of 1 minus. So you can write down this result, minus I and I becomes 1 and 4 pi by epsilon, 4 pi by epsilon into epsilon divided by 2 square root of 1 minus square. So we have the result 2 pi by square root of 1 minus. So this integral is 2 pi by square root of 1 minus. So we have integral 0 to 2 pi d theta by 1 plus epsilon of theta is equal to 2 pi divided by square root of 1 minus square, if I assume so the general scheme is, when you have integral from 0 to 2 pi of some trigonometric functions, cos theta, sin theta, then write cos theta as z plus 1 by z by root 2 and sin theta as z minus 1 by z by root 2i. Convert the integral into complex integral where 0 to 2 pi is replaced as a unit circle, and find out for the resulting expression f of z what are the poles, and then calculate the residues, evaluate the integral. Second type of integral that I will show you today is an integral, an indefinite integral from minus infinity to infinity of some real function. For example, in particular I will talk about minus infinity to infinity sin x by x. Okay, in general I can write it as e to the power ix by x, or probably before that let me also start a simpler integral. Integral minus infinity to infinity dx divided by 1 plus x square. This integral you can solve it by substituting x is equal to tan theta and converting it into 1 plus tan square theta is secant square theta. So this is something which you can do by such a substitution also. Now just to get us some idea how to use this contour, let me redo this integral using a contour integration. So now I am going to say that I will use a contour for this complex function 1 plus z square. Okay. What kind of a contour? I must use a contour in such a way that one part of the contour should be this integral. So, if this is the complex plane, I can choose a contour from minus r to plus r, a contour like this, contour like this, and then eventually take the limit r tending to infinity. So here I have in this contour minus r to r, so let me call this as some gamma, that wing of gamma. So this contour integral is equal to integral minus r to r, integral minus r to r. On this, what will be value of z? Z equal to x, because there is no imaginary part, z equal to x. So this is dx divided by 1 plus x square plus integral over gamma. On gamma, so on this line z equal to x. On this z equal to r into e power I theta. R is fixed everywhere, only theta will change. So theta will go from 0 to pi. dz, so since z is equal to r into e power I theta, dz is equal to I r into e power I theta, I r into e power I theta d theta. So I have I r e power I theta d theta, that is dz, divided by 1 plus r square to e power I 2 theta. So this is my, now I have to evaluate this in the limit r tending to infinity. Now in the right hand side, if you see, as r goes to infinity, this becomes the required integral, and as r goes to infinity, numerator goes like r, this is bounded, numerator goes like r, denominator goes like r square, so whole thing will go like 1 by r, so this will go to 0, the limit r tending to infinity. So this is the required integral, minus infinity to infinity dx by 1 plus. So if I do a contour integration of this, that is exactly equal to the required integral. Now how do I do the contour integration? I look at what are the poles.